This is Team 70's presentation on our Global Emergency Autonomous Response System, also known as GEARS. Team 70 is comprised of Benjamin Chappell, Cole Kingery, Trevor Mormon, and Alex Wiseman. We were tasked with developing a robot that could deliver supplies to an area affected by a natural or man-made disaster. In order to accomplish this, our GEARS must be capable of navigating damaged areas while carrying cargo completely autonomously. Along the way, the gears must avoid and characterize hazards, which will be included in the map created of the gear's path. Implicit communication with the receiving community must also be considered, such as ensuring that the cargo's contents are clearly indicated. To begin, these problems were converted into engineering specifications that the team regularly referenced during the brainstorming and prototype phases of development to ensure the final gears adequately met the mission's needs. The functional block diagram was useful during the development of the physical components of the gears to ensure each of the components came together to form a functioning robot. The diagram also highlighted the importance of coding to ensure all components work together. The team's work breakdown structure, as shown, was converted to a Gantt chart that the team was able to approximately follow throughout the entire process.
When brainstorming, the team came up with several ideas on how to accomplish a basic frame design. All designs we came up with were capable of zero-point turning. The two-wheel design, shown on the far right, was the simplest, but also had the greatest chance of having balance issues if support sleds were not used. A four-wheel design using omni wheels, which have integrated roller bearings to allow it to slide perpendicular to the axle as well as rotate along the axle, would be mounted at 45 degrees to the frame to allow for navigation along the X and Y axes without the need for rotation, although they can still turn on a single point. The six-wheel design was inspired by the Starship robots on campus and would have a lower center axle as to not slide the support wheels against the ground, allowing for introduced error from unnecessary friction. The team decided to go with the two-wheel design because of the simplicity and practicality. The chassis itself had several requirements. The chassis for the Gears prototype requires a rigid structure to reduce the chance of critical failure during its missions. It needs a compact design to navigate the narrow passageways. It also must be capable of making zero-point turns to reduce the amount of error during navigation. This first prototype found in the picture had the Raspberry Pi sideways to shorten the wheelbase, but it made it unnecessarily wide. This also wasn't very structurally stable due to the lack of mounting points on the far side of the Raspberry Pi. After analyzing these flaws with our first prototype, we decided on making a second, improved design. This improved prototype was better in every way, plus it added more functionality to the Gears prototype. The Gears prototype became significantly narrower and shorter, as well as more rigid. The new orientation of the Raspberry Pi made it easy to remove for work, as well as allowed for more versatile mounting points. This made the battery capable of being mounted underneath, lowering the center of gravity, as well as more efficiently using what little room we had to spare. For propulsion, each wheel is driven independently by two different motors. This allows for symmetric turning. It also allows for zero-point turning along the center of rotation shown by the gold circle. Large, thin wheels were chosen to raise the chassis height, allowing for the undercarriage of the battery as well as minimal dragging friction when turning. The same logic is applied from turning to course adjustment. The revolution rate in degrees per second of the wheels are adjusted to direct the gears prototype in the proper direction. The sensor array for the Gears prototype included 3 ultrasonic sensors, 1 IR sensor, and 1 IMU. The 2 ultrasonic sensors that are mounted directly over top of the axles on either side were in the ideal location because there is no offset from front to back when rotating. These 2 are used for wall detection as well as assisting with the PID control system for navigation. The third ultrasonic was mounted in the front of the Gears prototype to allow for front wall detection. The IR sensor is mounted on the front of the gears, allowing for the detection of infrared or heat hazards. This location was chosen because it would provide the most useful information, such as if a hazard is in the way of the gear's prototype, preventing further exploration of a path. The IMU was mounted to the top of the gears in the middle, but offset from the center of rotation. This mounting point was chosen to allow for the calculation of magnetic fields to be the easiest. The requirements for our cargo hold included the security of cargo. It must be easily opened by human force alone. It must be a simple design, and it must be 3D print friendly, meaning little to no support material is required. The final design used a sliding dovetail, which made the lid fit in only one way and keeps it from falling out. It also incorporates a lip on one side to restrict the movement of the lid. It has one hole opposite the lipped side, which allows for a Lego Technic connector piece or axle to pin the lid shut, keeping the cargo secure in all orientations. Finally, the extra material on either side allow for the cargo to be supported by the lid and offloaded using a single wheel on the back, which rotates on top of the lid. This offloads the cargo in a simple manner and keeps it close to the ground to reduce safety hazards.
LED lights were wired into the Raspberry Pi through Grove Pi wires and ports. They were connected to the wire heads, and then those were then connected to the digital port on the Grove Pi. A yellow light was used to display that the robot was still traversing the maze and that it was not currently ready for cargo drop as it still had maze to complete. The green light indicated that the maze has been traversed and that the cargo is ready to be dropped and has been dropped once the wheel took action.
For our cargo representation, the symbols to represent the 4 different cargo types were inspired by international warning labels found on chemicals. Initial brainstorming for recognizable labels included a heart with a pulse through it or a band-aid covering a blood drop, a tent with people under it or a house with a person within it, a water drop with a fork or a bowl, and a fire or a fire with wood underneath it. We conducted a survey which was posted onto the Purdue subreddit as well as the engineering students subreddit and asked which of the 2 available choices better represented the desired supplies. In total, there were 60 total responses choosing the 4 symbols displayed. We had responses throughout the United States as well as responses from Wales, Russia, Singapore, Bulgaria, and China. Overall, every symbol created was made using simple lines as well as minimal colors. This minimalistic approach would make them easily identifiable from further away, as well as easier to interpret.
These are some of the ethical considerations for making use of the gears. Generally, the amount, familiarity, and distribution of supplies is key to ensuring that the gears provides the maximum amount of relief while minimizing tensions to these areas. Isolated communities require special considerations such as respecting local authority. One solution which we thought of was by having the gears bot automatically end its mission if met with resistance from the local populace. Communities in conflict also require special considerations, such as ensuring supplies go to civilians and not to the militia. However, this is a more complex issue which would require different decisions and actions per each individual case.
Planning the software was incredibly important. We broke down the total code into smaller chunks that could each be contained in a few functions in their own file, and then mapped out the interactions between each of the distinct modules. The original design can be seen to the right, with a sample of some of the descriptions to the left. Over the course of the project, a few minor changes were made, but overall the structure allowed us to compartmentalize the software into far more manageable chunks. In addition to the organization of the chunks, we also opted to use the open source version control software Git. Git gave us the freedom to make mistakes in our implementation while still maintaining backups of all of our work throughout the semester, as well as allowing simple code transfer to the Pi. There were a total of 250 commits made over the course of the project. Shown above is the initial branch structure that was planned. We followed this structure until the very end when we added a few extra branches to manage the merging of all of the branches into one main loop. In order to store many of our major constants, we created a robot object. This stored everything from our ultrasonic ports to the BrickPy object to the root of the maze graph structure and the backtracking queue. Having this one object meant we only needed to pass one parameter into many functions that would otherwise require a large number of constants, while still keeping all of the information in a central location for easy experimentation.
Creating read functions for each sensor on the Gears robot. Whether it be for the IMU, the IR sensor, or the ultrasonic, read functions were made so that they could be called from outside code and the data values for the sensors would be output. This allowed for seamless use of sensor tracking, and so that values could be used in various places throughout the code and would not have to be implemented multiple times, allowing seamless integration.
For controlling the motors, a number of basic motor functions were created. These allowed us to create custom lower-level instructions rather than needing the actual BrickPy methods. This abstraction aided in coding efficiency as we continued into some of the more complex parts of the project.
The driving software of the gears was split into propulsion and turning. Propulsion works via a mixed system. The function steps the gears forward 1 unit of the maze, in other words 40 centimeters. However, if a wall starts being sensed or stops being sensed on either side, then the function will utilize this change to recalibrate the forward distance of the gears. The main turning function can turn the gears precisely to any degree, either clockwise or counterclockwise. The 90 degree and 180 degree variants were created to simplify other functions that commonly required these two types of movement.
We implemented a modified PID system in order to stay between the walls of the maze. Featured above is the PID for when a single wall is missing. We modified it so that the integral error would be negated, creating a force pulling the robot back to being straight. This largely prevented error buildup over time, as otherwise the robot would start to oscillate even when starting with small amounts of error. To keep track of the hazards, we created a hazard object, which stored all of the necessary information for one hazard. These objects would then be stored in a list, which is a field of the robot object, allowing for simple access. The string converter method allowed direct printing of the entire hazard object in the correct way, making the hazard output far simpler.
The hazard sensing software of the gears required both detecting magnet hazards and heat hazards. Detecting magnet hazards was accomplished by rotating the gears such that the IMU was closest to the left, front, and right maze units. The magnitudes of these measurements were compared to determine the direction of the magnet. An overall magnitude cutoff was added to increasing the speed of the gears by only performing this check when a magnet is sensed in an adjacent maze unit. Heat hazards were detected via an array of 3 IR sensors pointing to the left, front, and right of the gears, and are read from when the gears enters any new maze unit.
In order to navigate the maze, we created a tree structure using a custom graph object. Each node would have a maximum of 3 children, right, front, and left, representing the 3 potential paths out of any given hallway. 3 pairs of flags would also be set, indicating whether a given direction's path exists and whether or not it has been explored. Each node also stores the length, indicating how many cells it takes up, as well as its parent node to allow for backtracking. A sub-object was also made to store hazard nodes, which would store the type of hazard as well as the associated hazard object. This structure allowed for abstracted maze navigation as well as far simpler maze mapping. The navigation processes utilize the graph structure to decide which direction to go to and eventually build the tree representing the entire maze. Above are 2 snippets of the code, one for normal navigation and another for returning to an intersection with existing and unexplored paths when a dead end is reached, known as backtracking. Normal exploration simply sets a child of the current node to the resident direction and sets the necessary flags for the current node, then sets the current node to be the new node. Backtracking travels back up the tree until it reaches a node with an existing and unexplored path, which it then returns and chooses the next path to be explored. With all of the abstraction of the maze navigation, we then needed some way to transfer all that information into instructions for the robot. Matching orientation merely involved knowing the robot's current direction and the orientation of the target node, and then simply turn the robot to one direction or the other when applicable. Backtracking first turned the robot around, used the inverse direction of each of the nodes to get the robot back to the target intersection, as well as turn the robot towards the new direction. Backtracking utilizes a first-in, first-out queue, originally filled in the maze navigation methods, to know the exact path backwards that the robot would need to take. Once we had navigated the maze, we now needed to build the maze. This involved first determining the size of the maze, then filling the maze matrix with the appropriate values. This was done via recursive pre-order traversal. Finally, the entire maze would be exported to the proper file where it could be easily read by anyone.
A drop code was made. This code checks for all walls being dropped around the gears robot. This indicates an exit, which then turns a wheel connected to the motor, which is touching the cargo in the back and is then output off the rear, ready for the people to use it. External communications code is outputting a yellow light when it is traversing the maze, and then when walls are dropped and an exit is triggered, the green light is output indicating the cargo is ready to be used. The design for walls and sensing uses stopping value. The stopping value is generated from the ultrasonic value at the start when it is calculated at the front of the maze. From this, data is collected at each sensor, which is then given to the logic. If the data value collected is greater than the stopping value, then a 1 is added to a list. At the very end, a list of 1s and 0s is returned for use. The 1s show a wall and the 0s do not, and this is used later to recognize if we are too close to a wall, too far from a wall, or if there is no wall at all.
The main event loop stitched everything together. It first moved the robot forward one cell unit, searched for any hazards that might be in its way, then took readings on the surrounding walls. Using all that data, it would then go through one iteration of maze navigation, and then follow the associated maze instructions. Once the maze was navigated, it would activate the green light and dump the cargo, as well as output the maze map and any hazards information.
Features many positive attributes. One being software. The systems-oriented organization allows for simple testing of the individual components of the robot. This allowed us to make sure that they were functioning correctly. The robust navigation and mapping allows for a simple expansion of functionality when the gears is scaled up to be used in hazardous situations. The robot driving and navigation is effective in getting gears through a hazardous area. The chassis is also a big benefit. Its condensed nature allows movement in narrow spaces, avoiding wall hazards. This condensed nature also allows for zero-point turning, so it is nimble through corners and tight spaces. The cargo is also a big part in our robot. Cargo deployment is simple and effective, and the gears clearly indicates it's dropped cargo through a green LED light. However, the robot does have some negative attributes. One being low clearance. It's not a problem at demonstration, but could be impactful later on, as we do not know if the terrain is always smooth and flat. And the performance from this varies based on this terrain. At the demonstration, it was performed on a flat, smooth, and level surface. Rugged terrain and gradients would require adjustments to the feedback control system so that no large amounts of air were accumulated. Speaking on large accumulation of air, if the robot was not in the middle of an intersection, a turn can cause large amounts of air to enter the PID system, dramatically worsening the robot's performance. This leads into imperfect feedback control, as the current feedback control system fails to adjust when beginning with a high air. The system is also highly reliant on standardized walls being 40 centimeters apart throughout, and so it would need to be changed later so that it could adjust to changing wall conditions. Here's a video of the functional demonstration of Team 70's gear robot.
Big fail.
Please don't fail.
I can't see it, so I'm going to stop. Oh, that might not be good.
I got it. Come on. Oh, yeah.
Oh? What?
As you can see from the video, our Gears robot performed very well in our prototype maze.
Big fail.
In conclusion, we completed 4 out of the 5 checkpoints with our Gears robot throughout the maze. A map was also successfully output. However, with these great conclusions, there are also areas of improvement to be worked on. If we were to improve this later on, we would integrate global positioning, integrate a gyroscopic orientation tracking system into the PID system, improve PID control to functionally eliminate air, refine hazard detection so that more would show up and we'd have a better mapping system, and refine mapping and robot control so the robot can be the best it can be. In conclusion, Team 70 is excited for this robot to be used and scaled up so it can be used in disaster times and help those in need.